Thank you, Iris, for that kind introduction. Thank you very much. Thanks for the invitation to your forum. And yes, I changed from Dortmund to Bochum, which is maybe not very common, but I only changed university, not the soccer team. Yeah, so that is very important. Okay, ladies and gentlemen, thank you very much. And it's a pleasure for me to at least inform a little bit of what we are doing and what we are planning in creating a digital ecosystem for AI-based robotics. It's mainly about the research project we started around half a year ago. So it's a lot of things we want to achieve, and some of the parts we already have done, and that is what I want to tell you today. So that Project ROX is built upon mainly two pillars. So one pillar is realizing robotic solutions by the help of AI. Of course, we can discuss later on why that is necessary or maybe helpful, because as you heard, I'm a mechanical engineer and I'm building up robotic solutions now for 25 years. And AI is, at least in some parts of that, very new. So, for example, programming of robots, automatically programming of robots, it's a rather new approach. We started with that maybe 5 up to 7 years ago. But there are, of course, or there is the use of AI, for example, by using vision systems that is rather old. So I used the first algorithms in vision 20 years ago together with a company in Germany, Ruhr, building sanitary fittings, for example. You know that from the inventory of your bathrooms, for example. And there we already used AI solutions for the interpretation of pictures we have taken by camera system. So that is not pretty new, but of course AI in robotics is really booming, and that was the reason why we set up that project. So one pillar is creating a lot of robotic solutions by the use of AI, and the other pillar is what Iris already mentioned, is to build up an ecosystem in which we can exchange technologies between users, between vendors and end users. I will first of all start with explaining what we're doing in those robotic solutions, and after that I will introduce that establishment of such an ecosystem. So that is the project structure. We don't have to look into detail in this one, but maybe we can see, no, we cannot see. You can see the laser pointer, at least a little bit. And that is what we see here. So that is the first pillar, is creating several use cases by the use of AI in robotics. And that is the second one, building up that digital ecosystem. And of course, there are some additional tasks to perform, like defining semantics, developing special kits. I will explain later on what that is. And of course, we have to take care of dissemination, internationalization, and creating a long-term perspective for the project. This is a project consortium, and what we see here is that, of course, there is a robotics manufacturer, ABB in this case. There are a lot of integrators like Roboception, like Robomotion, and Sotec, for example. There are also end users and developers of different technologies like Siemens, integrators, or component developers like Schunk, delivering gripping technology for robotics. And also some new companies on the market like Yardstick Robotics. Yardstick Robotics belongs to Rheinmetall, and they are producing new robotic solutions for the production of, in that case, weapons, for example. And we have some research institutes in this. Let me go back. We have some research institutes in that consortium, like the DLR, the DFKI, and Fraunhofer Gesellschaft, that is the IPA in Stuttgart. So, and what are the approaches? So we have different robotics approaches from those different disciplines we have. You have also seen we have pharma industry inside this consortium. So we have a lot of different companies with different interests in robotic solutions, and therefore we have different use cases. And one of the first use cases we take care of is loading and unloading of trucks. And this is a very sophisticated task in logistics. And here we have to, or the aim is of course to use autonomous mobile robots and autonomous forklifts that are products we have in our ABB portfolio, forklifts, but not fully autonomous. And then of course our interest is to make them autonomous, autonomously working, autonomously unloading a truck. And the question is, what is difficult in unloading a truck autonomously? Is that a challenge? As you see, those drivers of those forklifts, they're doing that very, very fast, very sophisticated. They just manage it without any problems and without, or at least with very less damage. So it's sophisticated because there is somehow an unstructured environment in that truck. We have a lot of different parcels inside the truck. We have a lot of different products inside the truck. So our autonomous forklift has to detect that, has to detect the pallets automatically, has to move inside that area automatically. And that is something we believe AI will help us, especially in combination with vision systems. Same in warehouses and production. There we also want to use those autonomous forklifts. And even outdoor, so coming from outdoor to indoor and the other way around, which is also a challenge because we have to cope with obstacles in between, and also communication is sometimes somehow a challenge, coming from indoor to outdoor, for example. Second use case we are taking care of is picking, packing, palletizing in warehouses. And here the challenge is again having goods and a high package variety. So a lot of different products, a lot of different packages we have to deal with. So package identification, again, with image processing is very interesting for us, but also then how to program the robot to grasp all those things. So post-estimation grasp planning is the next challenge we have to solve. And also if you put objects on a pallet, for example, to plan and create a stable and compact packaging pattern on that pallet. Also very sophisticated, where we think we can make use of AI solutions. Another challenge, perception, of course. We will have that also in the other use cases. Developing gripping technology and combine that with software tools for grasping and packing is also something we have to take care of. Then third use case is kitting in production. And here is the aim to establish a generic robotic picking solution for a very broad range of parts. So you see mainly the tasks are coming from logistics and try to serve logistics where we have extreme variety of components. And that is our challenge here. Another part of that third use case is to address that problem we know since decades in robotics automation, and that is dealing with high mix, low volume, because our challenge in the past always was if we have very high mix, low volume, that it's economical and not feasible to use robots or robotic solutions for that. So therefore, again, perception comes into the place to solve that in detail. Now let's go to the next one. And also developing, and that is what we can see here, by the use of very sophisticated and new robotics kinematics, solve other tasks in robotics like transportation tasks in logistics, and that is where we want to make use of this robot. And here again, AI functionality for the training of such a robot, for stabilizing such a robot, for working in unstructured environments in logistics is the task we have to solve. Then you see something I will dig deeper into later on. Oh, sorry, there is an automatic slide presentation. Is the development of such a multifunctional robot. That is what we as ABB are taking care of. We want to have a mobile robot with a lot of functionalities which can serve totally different applications. And the first one we want to address with such a robot, this is only a prototype, so it's not commercially available. We will develop a commercially available robot in that project. Let me just stop that. So now it should work. And first of all, we want to use that robot in laboratory environments. That is a need which came up in Corona, where a lot of blood probes, for example, must be examined. And the hospitals had a lot of trouble in serving all their stuff. And therefore, we want to use robots in pharmaceutical production plants, in laboratory environments in the future. And therefore, we want to have that mobile platform with a robot on it with a lot of abilities, of course. And there again, that is something we will see later on, we need AI. Fourth use case, the commissioning. So use AI to speed up and reduce costs during commissioning phases, and or if we have to reconfigure a robotic system, also use AI. You know that using large language models, for example, for automatically create programs for robots, for other control systems, it's working quite well, and that is something we want to exploit in this use case. So question, of course, is, yes, then we have defined use cases. We have companies which are interested in a solution for exactly that use case, but how to generalize that? Because we're talking about a research project, and the main idea, of course, is to reuse all those developments for other scenarios. And that is something which is very important, because our idea was, first of all, start with real use cases and real demands, and then generalize that. So we will develop software components, generate generic software components, and then deploy software assets which you can use for also other use cases. So coming from concrete solutions to a generalization and deploy them for the use in also totally different tasks. That is the main idea. And then we come to the idea of the ecosystem, because we want to deploy those functionalities to at least a lot of customers which can make use of that. And if you just have a short look on the ecosystem we have in robotics, then it's well known. We have manufacturer of robotic components like we are as ABB. Also robotic components like Schunk as we have as a manufacturer of gripping technology. Then we have system integrators bringing all those components together, gripping technology, robots, vision technology, creating cells which really have functionality and can solve problems. And then we have end users, for example, like automotive industry and others. What is coming up is that we have a lot of companies which would like to provide services, and that is coming out of the software domain. So providing services like AI functionality as software to this ecosystem, to that very simple ecosystem we know already. So, and the idea is to integrate those service providers which can provide value-added services within that ecosystem. Using as a software approach DevOps from development in combination with operations, but I will skip this one because the main idea here is that the providers can, about their private storage, can deploy assets. We need connectors. how to connect the assets those providers are creating to our ecosystem. Therefore, we have, of course, standardized asset definitions and a digital ecosystem concept. We have those kits we have already seen in one of the first slides, which is a list of assets, the asset configuration, the connectivity, the deployment instruction, and dependencies to other products in that ecosystem. And on the other side, we have again a connector, and the consumer can then make use of those assets in his own application. For example, using a software asset from a provider in his own robotic solution. I will be more concrete on that later on. So those kits will manage the share of data in that ecosystem, will enable download and upload of different AI models those companies will provide, will deploy software, for example, on edge devices, will monitor data via cloud-based apps. That is the reason why we have T-Systems in that consortium, because T-Systems is providing the data infrastructure for this project. And why are we doing that? Why is it necessary to create such an ecosystem, and who will serve that ecosystem? Who will be partner in that ecosystem? That is also very important to see, because there is a huge initiative. I will explain that on the next slide. European initiative, which fosters to creating such ecosystems. And our main idea, of course, is to have an ecosystem where we have ultimate authenticity and trust. So an ecosystem you as a company are willing to use because you trust in that ecosystem. You trusting that that ecosystem will respect your intellectual property, for example, which is very important. And that you really can drive as a company, as a software company, the business with your own products without any losses of money due to misuse, for example. And of course, we want to have data protection in line with European standards, which is also very important. So if you see, so where is the main development of AI and of such ecosystems? We find that in the US, we find that in China. And the question now is, would you like to trust the ecosystem in the US? Would you like to trust the ecosystem in China? Or would you like to trust the ecosystem we built up in Europe relating to European standards? I would prefer the last one. So that is the reason why we enclose our project in that European initiative, creating a European ecosystem for the transfer of products, of software developments, and of AI, which also deals with transparency, openness, and modularity, interoperability, which is very important for us, that this ecosystem will really work on later. And that is the European initiative I already named. It's called IPCEI ZESS. And this central initiative for Europe tries to build up the world's first multi-provider cloud edge continuum and realize all the things I explained already. So to have a platform where we all trust in and where we can exchange our software products and have access to functionality over that cloud edge continuum. So I do not buy a software, install it on my computer. I have the direct access via the cloud infrastructure, which is, for example, hosted by T-Systems, and use that functionality with my robotic solution without creating such a software by my own. So I, as ABB, will make use of that software of those providers, and I have a very secure access to that software, and also the business model behind that, so how to pay for that, how to pay the provider for that via that ecosystem. So that is the main idea. So now just going into one example, because that project has a lot of developments. So we have around, actually run in 25 special developments, and I will present only one of this. And that is, now the battery, it still works. And that is what we are doing with our mobile robotic system. So we have seen this one, that is our prototype in principle, so that you have an image how that could look like. And our idea now is to build up a functional robot in laboratory automation. And that one shall serve all the things which are now done by human operators. So in that laboratory, the whole laboratory environment is built up for humans, not for robots. And we cannot change that from today till tomorrow. So we have to work with our robot in that infrastructure which is built for human operators. And we will, in the future, have also human operators serving that infrastructure in the day. And we can make use, for example, in the night. And maybe we have also collaboration between robots and humans in that environment. So we have to deal with that unstructured environment. And only one task in that unstructured environment is to detect all those different laboratory containers they use. And they use, only for blood probes, you have around 150 different containers. 150 different containers only for blood probes. And if you have to take other things, you see there is a huge range. So there is no chance for us to train all those things by hand, manually, hard-coded. So our robot must learn in his environment and must adapt to all those different products we have to handle. In this case, we're starting with the capping, decapping process, so how to open these containers and how to close those containers. And there are some which can be screwed, there are some which can be flipped, so totally different opening mechanisms, and we have no clue which container is how to open. That is something our vision system in combination with AI has to solve for us. And that is our first approach we are doing right now. So that is the whole setup of the system we want to use. And I can just go through some components in detail. So first of all, starting here, so we need vision. We need a vision system for sure to see our environment. And what we are using is stereo vision. In this case, it's a depth camera, which is directly mounted to the end effector of the robot. Stereo camera system. Most of you may know how a stereo camera works. So it calculates the depth by measuring the difference in pixel positions. Therefore, of course, we need two cameras, the left and right camera, and then we can use trigonometry to calculate the depth. And after that, we can make a pixel matching between left and right camera, and then we can detect the object in principle. And by the way, also that pixel matching of that camera and of the provider of that camera uses AI. So that pixel matching uses a combination of convolutional neural networks trained on the stereo images to improve these to improve the extraction of the features. And furthermore, we using an edge device that is the Jetson Nano Orin Super. That is a product from NVIDIA. As we know, we can calculate very good on those architectures, artificial intelligence. Therefore, we're using that one, and it's connected directly via Ethernet to the robot. And with that device, we are able to calculate the AI or the, just go one back. And of course, on an additional workstation, the AI models are running and the training data, so the images are stored. And that device directly is connected to that workstation. So here we see the object, or one of the objects we have to detect, such a laboratory container, and we have a scene, we have a 2D image we take, and the result is then the object ID, first bottle, the confidence that it is that one, and a bounding box around that, and then we can get the information where that object is in our scene. So now we have to build up a custom object detection model because our scene maybe looks like this one. So we need an annotation process of all the different bottles we have. And we are starting with a manual annotation process, so manually defining at least the first 15 different bottles. That is what we are doing here. And after that, again, we are using AI that is integrated in that annotation software. And that software then is doing the annotation of all the other bottles automatically. Jetzt ist die Batterie doch wieder da. It's doing automatically. And what we have to do afterwards, for example, doing the annotation of 150 containers in this case, but we have, of course, much more. Then we have to check if the annotation of the AI model is done correctly. So we have to verify that information, but that is much more easier than doing the annotation by hand. And then we see in this case, we have worked on 450 images. In one image, we have in average around 5 of those containers. So we have more than 2,000 annotations here. And you see not equal distributed. Bottle 1 we have nearly 1,000 times. Bottle 3 only a fourth of that. And what we then have to do with all those pictures, we have to do an auto-orient. We have to stretch it to a special format because otherwise the software cannot work on that. And then to make it more stable, we are doing a rotation, 90 degrees clockwise, counterclockwise. To make it more robust, we have a rotation between minus and plus 15 degrees. And we also manipulate the brightness plus minus 15%. And then we have a very robust system. Then the split for the train set, 990 images, 60 for the valid set, and for the test set, again, 5%, 60 images. What we then did, we used 2 different approaches. First of all, we tested YOLO. That means, or stands for You Only Look Once, and it's a software for object detection. And that one is running quite well on that hardware. It's specially developed on that hardware. It's a CNN-based architecture. And we tested that one, and that are the results with the sets we have seen beforehand. And as we can see, regarding precision and also regarding recall, we are quite nice. So the precision is close to 100%, the recall close to 98%, which is for a first step, it's not bad. But what does that mean in real? Those percentage values in real mean, and if we have a look on the diagonal, that's the good case, because here bottle 1 is detected as bottle 1, bottle 2 is detected as bottle 2, but that is not always the case, because we can see here bottle 4 is recognized 4 times as bottle 3. And that is, of course, a problem, because in that case, we will collide with the object, we will not grasp it correctly, so we will not handle it correctly, and maybe then we will waste a blood probe. And the patient has to come again, delivering his blood, and maybe that will cause some delay, and then maybe it's critical, maybe it's also health critical or life critical. So that is no option to fail here. We have some other failures in that, for example, that bottle 3, for example, is detected as background. That is also a problem, because then we will not grasp that bottle, but nevertheless, we will not destroy anything. So we will see that bottle will remain on the table, for example, and we have to proceed afterwards manually. So that are errors we can deal with. Those other are not good to handle. So after that, we tried a second approach. And here we used a real-time detection transformer, and that combines convolutional neural network backbone for feature extraction. And we used that one with much better results, like you can see here. So here the precision is, again, very close to 100%, and also the recall is close to 100%. And if we see what that does mean in real, we really detect all the things like they really are. And we have only one failure in that, and that is this one where we detect bottle 5 as bottle 3. So close to the aim without any failures, which is great. Now the question is how to improve that and also get rid of this one. We can extend the training sets, that is what we are doing right now, and see how we can get rid of that one. But nevertheless, that is maybe something we could accept because also the human operators are doing mistakes in their work. Just go that slide back, because what we see here, what we can see here, and if we compare that to the other model we have used, we see that the training time, it's longer, more than double time as the first algorithm had, and also the resulting model file is 3 times bigger than the first one. So that is something then we have to cope with, that we need more calculation power or more calculation time, depends what is critical here, and that also working on those models is consuming more time and more space. Nevertheless, of course, that is something we can handle, but now we have a very small model in this case because we're only talking about those 150 different models. Okay, so that is just to get a small impression, what does that really mean, working with AI to solving those robotic problems we have? So to increasing gripping precision and just to allow the robot really to have perception, to realize its environment and really to grip objects which are namely to be degripped by human operators. And then we have some another things to do, of course, with the matching of the point clouds, that we really can grasp, have the right grasp position of the object. That is something in addition. Just very, very fast, the outlook. There are other, I will not go into detail into that, there are other technologies coming on the market, like this one from NVIDIA Research, which is advanced point cloud generation with foundation stereo. We evaluated that at least a little bit, and that seems to a very good approach to use that for the detection of the products we are aiming at, like those containers, for example. And there is also another possibility of doing the grasping, so not directly recognizing the grasping position at the object, just, for example, trying to find the medium center of the grasping object, and then just trying a totally different grasping approach, which could also be helpful to do. So a lot of possibilities just to solve that one issue we have. And in all those tasks I have explained in the beginning, we have a lot of single research projects to solve each task. And then you can see all the solutions which will be developed here. It definitely makes sense to bring them into an ecosystem where everybody who wants to make use of that can have direct access, and also a business model is underlying which is valid and which can be used. Because we are familiar with using open source software, and we pay open source by delivering our results also as open source. That is something which is not feasible doing like a company like we are as ABB. And also for all the other companies, it's not feasible only going by open source. So we need realistic business models behind that, and we have to take care that we have the rights, and that is also very, very important. For example, talking about licenses, that we have the rights to use that software tools, to integrate those software tools, and that we have the rights to use all the results which we produce with those software tools. So therefore, it's very important to have that ecosystem which also takes care of intellectual property and the business model itself. So that was at least a short introduction in all the things we have to do and we have to solve. So thanks for your attention, and I'm open for questions if there are some.